Welcome back to the PVOP podcast. Today we have the pleasure of having Vatcraft as the guest of our episode. So, founded in 2012, the Vatcraft group initially focused on trading photovoltaic components. Today, they are a prominent European distributor for major international corporations and operate in two key business segments, so distribution and product integration. So Vatcraft specializes in inverters, photovoltaic modules, and electrotechnical accessories, while also offering integrated system solutions, particularly in the system monitoring and telecontrol technology. And today, they are here as a PVOP partner and showcasing a little bit about their solution. Hello, Alejandro. Once again, thank you so much for attending this episode of the PVOP podcasts. So today we're talking about your solution, which is AI-based smart control system for PV plants with batteries. So this solution is done with Vatcraft. So I wanted to explore a little bit more about the sector first of all. So with the rise of renewable energy, how would you say batteries and advanced control systems are reshaping the grid's capacity to handle intermittent supply?
First, thank you very much for inviting me here, Rui. I think before we answer that question, we have to examine a little bit exactly how renewable energy, specifically intermittent renewable energy, affects the grid. So traditionally, our grid has been designed to support variation mainly on the demand side because traditional generation sources, the synchronous machines like gas, coal, and hydropower, they have the ability to increase and reduce generation on demand, and they can accurately respond to these variations. So we can increase generation or lower it depending on how the consumption is operating. However, when we introduce renewable intermittent sources, now we also have variation in the generation side because wind and solar, they're actually dependent on nature forces. And well, they can be very accurately predicted nowadays, especially as they become closer, but they can by themselves, they cannot be controlled. They can maybe be lower, but they cannot be increased on demand. They depend on wind and sun. And as more synchronous machines are also displaced because we have generation consumption. So if we have more renewable energy, that means that other sources such as coal and gas and hydropower, they start becoming displaced and they become, let's say they go out of the mix in that moment. That also means that we have less generation that is capable of responding to this variation, which is now doubled in the generation side and the demand side. And this can weaken the grid response. There has been several ways that grid operators can tackle this. For example, such as tools like forecasting and demand-side management. And these have helped integrate safely a lot of renewable energy. However, as the quota increases and we approach the 100% renewable penetration in certain hours, these capabilities by themselves, they become insufficient and more is needed. And this is not the only thing, but we also need grid stability tools that help increase the inertia because that initial response from synchronous machines is becoming less and less. So these where batteries come in. Because batteries, not only can they provide energy on demand, they can store the excess energy during peak hours and they can use it and dispatch it according to the demand. But also when we integrate grid forming technologies, we can also provide essential ancillary services. So we can not only provide that energy on demand, but also we can have frequency regulation, inertia support, voltage support, and black start capabilities. So we are compensating the absence of these synchronous machines while maintaining our grid renewable.
That's great. So going back a little bit to the challenges that they face. So what challenges do operators face when synchronizing energy storage with real-time generation and demand patterns?
Well, I believe that mainly the advantage of batteries that they have, and it is that they can both act as loads and as generation sources, since they can absorb and deliver energy it also becomes a challenge because we have to rethink the way we operate the grid. Because now we have these capabilities, but how do we choose? Meaning, when do we charge and when do we discharge to take advantage of these capabilities? Here it becomes important to have a degree of certainty of how much storage is going to be available, and this is important in order to have a reliable operation of the grid. And here, the variability of renewables is a challenge because it also represents a viability of when we're going to have energy available. Right now, we have predictive models that are implemented in the planning of the grid, which consider grid and solar, and this is really good and important. So here, an energy management system that can implement these models in their algorithms is a great advantage. A model that can predict when there's going to be accidents, so when they can charge and when energy is going to be needed, so they can charge in advance. Additionally, operators, they have to ensure that storage systems can adequately respond to sudden changes in demand or generation due to a cloud or a PV plant, for example. So integrating multiple data sources like weather forecasts, grid load data, and battery state of charge, these will require some sophisticated algorithms and high computational power so that we can overcome these challenges.
Okay. And one of the things is integration with existing systems. So how can these smart systems, these AI models, integrate with broader grid services like frequency regulation or demand response programs?
Well, first to comment that the grid has been following this trend of becoming smarter and not only consisting of loads and generators that change according to these loads. We have integrated a lot of advanced mechanisms like advanced metering infrastructure, green interactive efficient buildings that allow for bidirectional communication between loads and the grid. So an EMS, energy management system that can respond dynamically to grid signals and market conditions is essential here. So, and here we can have smart systems that both have AI or without it, that they can actually optimize this energy usage at buildings, for example, or industrial facilities, and use also demand response with energy storage, so that consumers can increase and reduce their consumption through their batteries and provide flexibility for demand response programs when the load consumption is not flexible. Because if I have a flexible load consumption, I can respond to the signals from the grid and lower it or increase it. But if I don't have that ability, then I can do it through a battery, which would essentially increase or decrease the load consumption by displacing charges from one moment to the other. And this RAT system, for example, is a mechanism as such that is currently implemented in Spain, where basically consumers, they give a portion of their load to the grid. So they basically say that I'm going to put like this amount of megawatts and I'm going to make them flexible. So I can reduce my consumption during these hours where you need it for 3 hours straight in 1 megawatt or 2 megawatts. And these in loads where they do not have the flexibility, but they install batteries, they can provide this service.
And okay, that's very interesting, and definitely I think it could actually allow for a lot of more flexible consumption and these. But focusing a little bit more on the solution side. So how does this AI-based system that you guys are developing address like the complexities of, like, for example, managing energy flows, or even like managing the PV plants, the batteries, and the grid? So how does it combine all of this together?
Okay, so actually implementing AI helps to process better data that is essential for accurately operating the battery. So when you consider data such as weather forecasts, electricity prices, and the battery state of charge and grid constraints, when you process all this data, then you can more accurately respond to events. So for example, during periods of high solar generation, the system could prioritize charging the batteries or exporting energy to the grid if prices are favorable for this. Or during low generation periods, you can discharge the batteries to meet on-site demand or provide grid support. And the AI is continuously learning from this historical data and real-time inputs, and is improving the decision-making over time, ensuring that there's sufficient cost-effective energy management. So in this way, AI allows the prediction of risk instability events and demand surges, and you can preemptively prepare the battery to respond to these events. As a result, AI can coordinate rapid dispatch of stored energy for batteries when the frequency deviations occur, and it can also ensure a fast and seamless grid response, and also keep the batteries charged and ready to respond to demand surges.
All right. And what other things can this AI basically do in the long term for companies that want to acquire it? So does the system offer long-term optimization? Does it extend the battery life, and does it improve the return on investment for operators, for example?
Yes, first, like making the clarification that AI can actually optimize these functions. So an EMS and energy management system can actually function and implement these services without AI. However, AI implementation does improve that response. So basically, batteries they have a degradation that occurs over time, and this is because of usage and aging. This means that if you don't use your battery, it is going to be degrading anyway because they have a lifetime. So the most economically feasible thing you can do is to maximize the number of cycles that you're doing every day, because the more cycles you do every day, that means that the more energy you are taking advantage of, and less time degradation is occurring. So maybe in terms of years of the battery, it's going to be less years, but in terms of energy, which is actually like the monetizable variable and the variable that impacts CO2 emissions, we can get more energy from this process. So our energy management system, it optimizes return by maximizing the number of cycles per day. It takes advantage of solar surplus that would otherwise go to waste to curtailment, as well as peak value price fluctuations. And also by incorporating demand prediction, solar PV generation forecast, and spot energy prices, the system can ensure that the battery performs cycles. And this way we can maximize self-consumption and leverage peak value price differences. Also, discharging during higher price hours can contribute to the grid stability because the price signals of these hours also indicate a surge in demand, which is often met by fossil fuels. Additionally, the system is designed to participate in this RAD, as I previously mentioned. So this is an additional financial incentive for battery storage systems, especially where demand is inflexible. If we go to the technology, because our system is actually meant to function with the Huawei batteries, and this battery technology allows for full charge and discharge cycles, unlike other batteries that may not support this. So we can make full cycles more effective for maintaining battery health and performance. The result is that we have a higher storage capacity, which has an impact on the LCOS, which is really important if we're going to consider the long-term investment of the battery. And it can also optimize trading in markets with variable pricing, ensuring operators can capitalize on high price periods.
All right. So going back a little bit, so you mentioned that the system is designed to participate in the SRAD, and so it offers extra financial incentives for battery energy storage systems. Is that correct? Is this something that operators can benefit from?
Yes.
Okay, good. And okay, just to clarify it. And then what differentiates this solution from others in terms of ease of implementation or scalability for different project sizes?
Okay, so we can talk here about the battery solution and the control solution also. When it comes to the batteries, the AC coupling actually makes the battery much more flexible and makes it easy to seamlessly integrate with new expansions in systems. So if you have a PV plant already, since you have an AC coupling, that means you can couple the battery even if the inverters are from a different brand. And there's also a wide variety of ranges. So you can have in CNI, for example, commercial and industrial applications from 107 kilowatt hour, 161 and 250 kilowatt hour. And then you can connect these in parallel to get even higher storage capabilities. And in utility, you have 1, 2, or 4.5 megawatt hour, and soon a 5 megawatt hour battery, all in 20 feet containers. So when it comes to the EMS, to the control system, we also have a flexible system that can be easily scalable. So we have a master unit and an indefinite amount of slaves unit that you can deploy according to installation requirements. So if you have an expansion that is somewhere far, then it's okay because you can have a secondary unit that can communicate to the main unit. And so the solution is modular and adaptable, whether it's a small residential system or a large scale grid connected battery, DMS can meet the specific needs of the project. It also has a user friendly interface and pre-configured templates for common use cases, so you can reduce the time and expertise required for implementation. And it has a cloud-based architecture that allows for remote monitoring and updates, so you can always keep the system up to date with the latest features and requirements. So even if there is a regulatory update or there are improvements, if you have like the first version of this system, it's going to stay updated.
Okay. So, and how does it adapt to these regulatory frameworks or to these market specific constraints? Do you so it adapts by itself? Do you need some input from outside? How does it work?
Well, currently the system is designed to meet the regulatory and market-specific requirements that we have in the Iberian electricity sector. It is currently certified to comply with the net zero requirements that are outlined by the Spanish code. And so we can ensure grid stability by responding in under 2 seconds when it is necessary. This is only the first step, though, because the plan is to adapt the system to operate in other markets where Vatcraft has presence, such as Germany, Italy, and the Benelux area. And of course, the system can be updated. So if there are like regulatory requirements that are then demanded, so the system can be updated from um, basically from remotely, so it can always stay up to date. Also, we utilize meteorological forecasts that we collect data from satellites and local sources, so we can provide really accurate estimates of solar production and ensure an efficient charge and discharge management. And our system is connected to the spot market prices published by the OMIE, which is the authority that publishes these market information of the spot prices. So when we combine this data with customer profiles, we can ensure optimal operation of the system within the Spanish market. So it is really adapted to the current regulatory situation.
All right. And one final question. Can you give me one line or two lines regarding this solution and for PV plant owners and PV plant operators across Europe that right now have their plants and are struggling to keep the demand or have some trouble when it comes down to demand generation. So how can we ensure that this solution enables them to actually have these problems solved?
Well, I would say we have a flexible solution, a solution that is adapted for the local situations, and a solution that can also be adapted to particular situations that we encounter. So even if we found that we have a customer with a PV plant that has very specific situation when it comes to, for example, peak shaving needs, or that they have like some constraints, we have a local team and we're able to adapt the software so that the system can respond to the specific situation and be profitable for the specific market scenario our client is currently in.
All right. Thank you so much, Alejandro. Thank you so much for listening to this episode. If you'd like to learn more about the project and its solutions, please visit the pvop.eu website and join our community on Discord, okay? The link is in the description, and you can also follow us on social media on LinkedIn. We'll see each other in the next episode. Thank you.